The first part of the worksheet has us figuring out total resistance. You'll notice on most circuit problems, the very first step you have to do is solve the total resistance. So excuse my terrible handwriting. So we'll start with letter A here. So I've got a long end of the battery here, which is my positive end, and I've got a short end, which is a negative. Now, although we say that current flows from the positive to the negative end, we also think about charges as like little electrons coming out. So we can even think of the electrons coming out the negative end going towards the positive. Either way, some will come down the 7, some will come down the 5, and some will come down the 2 ohm resistor. They all have to turn around and go back to the battery, okay? Which means that they won't go back in reverse course. They can't go up 2 different resistors. So that means that there's some sort of way of averaging the resistance for all the resistors together. This is the one that has fractions involved. So I end up with 1 over R equals, and then 1 over each one. So if I had 4 resistors, I'd had 4 fractions. If I had 2 resistors, I'd have 2 fractions. So since I have 3 resistors, I put their values here. If they weren't whole numbers, I just use the calculator. But they are whole numbers, so I need to find a common denominator. 7 and 5 have a common denominator of 35, but that doesn't work for 2. So I'll just kick it up to 70, because 35 times 2 is 70. So 1 over R equals, well, 1/10 of 70, or excuse me, 1/7 of 70 would have been 10 sevenths. You know what I'm trying to say. 10 70ths. To get to 70, that's times 14. I know because 5 times 4 is 20. 10 times 5 is 50. So 20 plus 50 is 70. So that would have been 14 over 70. And then this one was going to be my easiest one, 35 over 70. Add them all up. So 35 and 14 is 49, plus 10 is 59. So 1 over R equals 59 over 70. Most common mistake is people leave it there, and they'll say that R equals this. And that's not true. That's 1 over R. So the very last step is to say that R equals, and then you do the inverse. 70 over 59, which comes out to be like 1.19. And then ohms. So there's a few things you should take away from that. I have a bunch of resistors. They are all here as huge integers compared to our final answer here. So 7, 5, and 2, when arranged in parallel, make something very small. And we're going to contrast that with B and C, where our resistors here are all in series. So in series, it's actually the easiest. You just add them up. So what's 2 plus 5? 2 plus 5 is 7. So 7 ohms. So automatically I can tell as my charges come out, they have to go through one, and then they have to go through the next resistor also. They don't have any other choice. They can't go another way. So that's why we can just add them. There's no any kind of fractions or anything like that to get an average value. Which means down here this would be 2 plus 5 gives you 7 again, plus another 7. So 7 plus 7 equals 14 ohms. So hopefully you've noticed a pattern. In series you have one pathway. This is why we say the current's the same. In parallel you have multiple pathways, and that's why the current has to split. And so your answers were, to go back and emphasize them, 1.19, 7, and 14. Whenever you have voltages or battery sources, or voltage sources or batteries, anything like that that are in series together, you can tell because they are linked together one after the other like that in series. You just add them up. So 3 plus 4 is 7, plus 6 is 13 volts. And the same down here. 6 plus 6 is 12 volts. When we get to physics 2, if you take physics 2, we can worry about batteries in parallel, but you should never worry about it. The rules that we talked about, these were the loop rules. Basically, if this added up to 13 volts is going to get used through the resistor. If this was 12 volts is going to get used through the resistor. In problem number 3, we have a circuit diagrammed here, which you should be able to visually identify as series. That means, again, whenever the current comes out of the batteries, It has to go through one to get to the other. This is how we can visually identify one of our rules where we said when you're in series, current is the same everywhere. So if I can figure out the current, which belongs in this column, whatever that number is going to be the same all the way up and down because it's the same everywhere in series. Well, let's go back and figure out what that is. So one of the first things I told you is usually you have to figure out the total resistance. These are in series, so just add them up. 10 and 20 gives you 30. 30 plus 30 gives you 60 ohms. Switch back over to black. Now that I know that this is 60 ohms and this is 6 volts provided, which was given in the problem, I can kind of zoom out, if you will, for a whole circuit kind of point of view and do V equals IR, Ohm's law. That gives me 6 equals I times 60. 6 over 60 would be 1/10. So I is 0.1. Alright, now that's measured in amps. So that means that this is, if I go back here, this is going to be in the way, I apologize for that, but this is 0.1 amp, this is 0.1 amp, this is 0.1 amp, and this is 0.1 amp. Because remember, current can't decrease, that would indicate charge is building up somewhere, which is impossible. It flows around the whole circuit and goes back to the other side of the battery. Well, now that I know 2 out of 3 V equals IR, I can just multiply across. So V equals I times R. So 0.1 times 10 is 1, 0.1 times 20 is 2, 0.1 times 30 is 3, and 3 plus 1 plus 2 gives you 6. And that shows you that all 6 volts were provided, were used. Alright, on question number 4, you can see that this thing's in parallel. Again, that means as my charges come out, they can go down one pathway or the others, but they won't do both at the same time. This means our math is done with fractions. So 1 over our equivalent resistance, or total resistance, whatever you want to call it, is 1 over 4 plus 1 over 6 plus 1 over 12. That gives me a common denominator of 12. So 3/12 plus 2/12 plus 1/12. So 1 over R equals 6 over 12. And then when you flip it, instead of being 1/2, R goes over to 2. Okay, well that's handy, because again I can do V equals IR for the whole circuit. So 6 equals I times 2. Current is now 6 over 2, which is 3. This is not series though, so I can't put 3 everywhere. But this is the junction rule, which means I have 3 amps here. And it's going to split up somehow. 3 amps will come back joined together here. But because it's in parallel, the opposite part of the rule is that the voltage is the same everywhere. So if I was provided 6 volts here, each little dot has 6 volts of energy basically that it can use. So that means this will be 6 volts, this could be 6 volts, or this could be 6 volts. So it's kind of like you have $6, and every little person has $6. So you either use 6 in lane 1, lane 2, or lane 3, but you don't go back there multiple times. So that means that these are the same everywhere. And now I have V equals IR. If you arrange that, you get I equals V over R. So 6 over 4 is 1.5. 6 over 6 is 1. 6 over 12, excuse me, is half. And 1.5 plus 1 is 2.5. Plus another half is 3. And then I forgot to show you power in the last one, but it's just I times V. So in this case, all you got to do is multiply the current times the voltage. And to do that on this one, it's 6 times 1.5, which would be 9 watts. 6 times 1, which would be 6 watts. And 6 times 0.5, which would be 3 watts. Okay, so why do we care about that? Well, these are correlated to brightness. So that would tell you then that if you had to look at all these light bulbs, looks like R1 would be the brightest, and then R3 would be the dimmest because of the numbers. And that actually makes sense, because if you look at the resistances, the least resistant got the most current, and the voltage was the same everywhere. So if most of the current goes to the least resistance, they'll get all the brightness, and then that means that the highest resistance gets the lowest current, so it would be the dimmest. And you're going to notice in a couple pages in your packet, we're going to get to problems where they don't even give you numbers, and they just ask you to figure that out. Or if they said like R1 was a third of the value of R3 and they were arranged like this, would be the brightest, well, you'd have to say just R1, because they're all going to have the same voltage, but it would get more current because it has such a low resistance. Alright, question number 5 has something we call a combination circuit. So that means that you've got these charges coming out of the battery. They have to all pass through R1. So key aspect in your mind is all the current has to go through R1. Then the current will split, and some will go down R2, some will go down R3. Then they'll come back together, and then they'll go back to the battery. So if I can figure out, here's my pattern, if I can figure out my total resistance, and I know that my total voltage provided, it says in the problem, is 120. If I can figure out my total resistance, that will give me total current, which I know is the same value for I here. That will help me figure out the voltage used here at number 1. Now if you remember back a couple problems, when you're in series, the voltage gets split up differently. So that means whatever voltage is left will be identical here in spots 2 and 3, because those two things are in parallel. And when you're in parallel, the voltage is split up, or excuse me, the current is split up, but the voltage is the same. So let's go back through and do some of the numbers then. So my total resistance, it's not 58, it's not anything screwy, it's not any fractions. It's kind of like this. R2 and R3 are in parallel. Hopefully I didn't just call out the right number and say that was wrong. Just follow the math. It's pretty late. Help me out here. So these two are in parallel with each other. R1 is not in parallel with them, so I cannot add it like that. So common denominator there is 60, so 3 over 60 plus 2 over 60 equals 1 over R, or RT. Add them up and you get 5 over 60, which is the same as 1 over 12. You flip that over and you get RT equals 12. So for this little portion, I'm going to circle in purple that has a combined or equivalent resistance of 12. Well, that comes in series with R1, so it would have to be 8 plus that 12 gives me a total resistance of 20. So 20 goes here. Well, that helps me with Ohm's law, because we know that Ohm's law says that V equals IR. So for the whole circuit, 120 equals an unknown I times 20. Well, what times 20 gives you 120? That'd have to be 6. So I know that 6 amps goes here, which means that 6 amps goes here. Because again, as it comes out of the battery, I'll use purple, all of it has to pass right here through R1. So that means it gets 6. Well, now I've got enough information to do V equals IR again. So let me erase this because I'm kind of out of space. Hope it'll let me erase. It will not. Fine. So V equals IR. I need to know how many volts are used at R1. So it's 6 times 8. 6 times 8 is 48. So I know 48 volts out of the 120 got used. Well, that means there's 72 volts left. And 72 volts will go either for R2 or R3. They're on parallel, what we call branches. So that means they each get the same. They're not the same as R1 because they're not in parallel with R1, but they're in parallel with each other, so they get the same as each other. Well, then the very last step is to figure out I, the current, for R2 and R3. I can automatically tell you that R3 will get more of the current just because it has less resistance. It's 20 compared to 30. So if I do I equals V over R, I do 72 over 30, and I get 2.4 amps. And if I do 72 over 20, I get 3.6 amps. And that kind of proves what I was just saying, that the 20 gets more current. But 2.4 plus 3.6 gets you up to 6.0, which is exactly how much R1 had before it split. And then it goes back together to be 6 again, which shows you the junction rule. So the loop rule and the junction rule are being shown because the loop rule shows that all 120 volts are being used, and then the junction rule shows that the 6 amps splits and comes back together without losing any. So I'm not going to answer question 6 for you because you should be able to figure it out based off everything we've already done. But question 7 asks about an ammeter. An ammeter, if you think about just the words that are there, it does something to do with amps, and meter means it measures. Well, it turns out that's just a shortening of the word amp, so it's like an amp meter, which means I'm measuring I current. Okay, so amps are current, so how would we measure the current? That's basically what an ammeter does. So you'll see it in a diagram where they take a circle and they either place it in series like that circle there, or they put it in parallel around something. And when I say around, notice how this leg is before, this leg is after, so it's kind of like it's hugging it. It's before and it's after, so it's around it. And you have to think back, okay, like, well, what would do each one? Well, if my current is the same everywhere in series, I'd have to put my ammeter there. And then if I needed something in parallel so it got the same voltage, that's how I would measure the voltage, so with a voltmeter. So there's going to be a couple questions maybe on our test, a couple questions maybe on the AP exam. It just depends. And it might not be the point of the question, it might be a small detail. But if it shows you like what would each one of these measuring devices do, rule number 1 is it doesn't change the circuit whatsoever. It's just there to detect the value. And then 2 is that's how you'd lay them out. Alright, so this is question number 8. And it's about switches and correct wiring. So please excuse my terrible drawing. But in every one of these circuits, it's really a question about what makes what's called an open circuit or what makes a closed circuit. So an open circuit is something like this one here, where there's not a pathway for the current to flow. So it's essentially just dead wire. And a closed circuit would be one like this one, where there's a pathway for the electrons or the energy, the charges, the particles, whatever you want to call them, to go from one side of the battery to the other. So what you have to do is you have to evaluate, in this particular question number 8, does the switch matter? And if so, what would it do? So the question says, which one operates correctly when the switch is closed? So first let's think about what happens when the switch is open as it is. So when the switch is open here, the charges, that's a light bulb by the way, a circle with a little squiggly in it, that's just an old school light bulb. Thomas Edison, think of that one. A little filament that lights up. No LEDs, no fluorescence. Those dots represent on A where the charges would go. So if the switch opens, it actually operates correctly. Now the thing that would get screwy though is what would happen if I close the switch. If I close the switch, the charges would come out. And when they got to this junction here, this switch now would be a straight line. There wouldn't be any open gate there. And so ignore that. Ignore this part of it now. Imagine it's just flat. The chargers would think, okay, there's 2 checkout lines. I can go this way and pay, or this way and get it for free. So they actually all go this way, and they just bypass the bulb and go back to the battery. And it's really the same thing as before. You could say that these 2 branches here, 1 and 2, are in parallel, so therefore they get the same voltage. And V equals IR. But literally this one gets no I, because this has no resistance. So if all the current went with the lowest resistance, or excuse me, most of the current went with lowest resistance, it just so happens here this one went on 100 to 0 split. 100% of the current went down the no resistance pathway. So to answer question 8, which one operates correctly when the switch is closed? Definitely not A. A was working when the switch was open, but then it got all jacked up when the switch closed. If you go back and you look at B, right now, B is down here. B doesn't even work with the switch open. The battery wants to let charges out this side, here, where I've drawn red, but there's no way to connect to the back side of the battery, where I'm dotting it red now, which means it doesn't feel that flow. Another word would be gradient. It doesn't feel the push from one side of the battery to the next. So that means that it can't possibly flow. So it's kind of like having a calculator with 3 batteries in the back instead of all 4. That's great and all, you have 3 batteries, but without the last one there, it doesn't work. So then you close the switch, and what ends up happening is that now that this switch is closed here, so again, ignore that part. Now that this thing is closed, the charges come out to the front, and they can finally flow, and then they have to make a choice. They could go this way and experience resistance in the light bulb and go back to the battery, or they can go this way and experience no resistance whatsoever and get back to the battery. So that's what ends up happening. Again, this is called a short. The charges go down the blank wire because these two branches here and here are in parallel, and again, no resistance gets all of the current. If you go up to C now, C with the switch open doesn't work because there's no pathway to get from the back of the battery to the positive terminal of the battery to the negative end because of the break that's there. However, when you close the circuit, now this is the correct answer. Which one lets it flow? This one. Now that I've closed the switch, charges flow nicely, they get used, there's no short circuit. It's basically how a circuit should have been used in the first place. And then A and D are very similar, where with the switch open, D flows this way, it's nice, it's perfect. Then when you close the switch, all that changes. The branch over there, this branch compared to this branch, so this branch has no resistance, and all the current says, wait a second, forget all this, I don't want to go that way, and it erases all that. Let me go back. And it says I don't want to go that way anymore, and they'll only flow this way and short out the circuit. So hopefully by listening to this question, you've realized the difference between like what a switch does and the difference between an open and closed circuit and what a short circuit is. Alright, question number 9 and 10 refers to this diagram where this is starting to branch from instead of those forward questions where it's like here's some resistors, figure out the total and then get the current and all that forward progress we're making. Now we're just going to have to solve it in a different order. So if I need to figure out the total resistance, I used to be able to do, because this is in series, and you should be able to figure that out visually, it would have been 50 plus whatever R is, gives me some sort of total. Well, I have two unknowns now, so I can't just do that. So maybe there's a way to work backwards to get, say, this number here, and once I know that number, then I can solve for my resistance. Or vice versa. Maybe I can solve for R some way. Well, it turns out that the gold one is the one we can solve first. I can solve for total resistance by doing just whole circuit V equals IR. So I'm zoomed way out, if you will. I'm talking whole circuit, not individual resistors. So for the whole circuit, it says 120. Well, what do I plug in for I? Well, remember, when you're in series, the charge comes out and has to go through each one. So if I know the charge here, that is the charge everywhere. So that means that my current is 0.5 because it happens to be in series. So what's R? Well, whatever half of R is gives you 120. So that means R was worth 240 ohms. And that happens to be the total resistance. So that answers number 9 for you. And then number 10, the answer would be right here. So what plus 50 gives you 240? That'd have to be 190. Alright, the very last questions, 11, 12, and 13, have to do with this resistor, or excuse me, this circuit. Because it has two different ammeters, it almost looks like a combination circuit, but it's not. It's still just something that's in parallel. So there's a couple different ways you can think of it. I'll show you the very short and simple way of solving every bit of information first. And then after you get that, you'll find a lot of information if you sit around and wait for the second way to think about it. So if you're pressed for time, the easiest way to do this one is to say these two branches are in parallel. So that means they both get the same voltage. So that means this thing gets 12 volts, this thing gets 12 volts. If I did V equals IR, I now have 12 equals I times 3. Well, 4 times 3 would get me 12, so I here was 4, which means if I had 5 amps total, then, and they were splitting and then going back to equal 5, it must be 4 plus 1 amp. So if I had 12 volts equals I times R, 12 equals 1 times an unknown R must equal 12. So that answered all of our questions. Almost. What's the total resistance? Well, the total resistance would have been the total circuit V equals IR. V was 12, total current was 5. R must have been 12 over 5. I guess I could have got a fraction or a decimal out of that, but it's not really worth it. The next question was, what's the current in A1? We solved for that. We said it was 4 amps. And then what was the unknown resistor? That was 12. Okay, then let's back up. We've done that. We got all our answers. Check, check, check. That's a pre-AP level way of going about this. I got all the answers through technical skill and not really understanding why. So let's beat this thing to death now. So let me erase a bunch of these marks and go back and get the exact same answers, if it'll let me go back that far. So the first thing that I see when I see A1 and A2 is I see a question that wants me to know the difference between series and parallel. So I'm automatically, I'm automatically going to see two things. I'm going to see this number here and think total circuit because there's no junction. And I'm going to see this one and see partial current because it's part of two parallel branches. So if I want to backtrack, before, the way that I solved for it was using V equals IR everywhere. I would argue that you could almost think of this in a different way in terms of what if I solve for it in terms of proportions. So, like, what do I mean by proportions? Maybe I'm using the wrong word. Think of it like fractions. So let's delve deep into this. So because it's in parallel, well, that's not going to work. Because it's in parallel, I know that 1 over R equals, and that's total equals 1 over R1 plus 1 over R2. And I know because I have numbers for some of those, we said the total resistance was, a second ago, 12 over 5. So 12 over 5 equals 1 over 3 plus 1 over our unknown R that's sitting there. Well, when I divide by fractions, again I have got to flip them. So that instead of being 1 over 12 over 5, that just becomes 5 over 12. Well, I need to take this thing then and turn that into a common denominator there of 12. So I've got 5/12. Multiply everything by 4, that's 1/3, plus some unknown 1 over R. So what plus, what plus 4/12 would give me 5/12? Well, I guess that'd have to be 1 over R equals 1/12. Okay, so then that would be another way of showing that R had to have equaled 12. So that was just a mathematical way of getting to it, like a second way. Now let's get up to the proportions thing. I was kind of jumping ahead a second ago. I have these two numbers, 3 and 12. This is weird, but it's not that bad, but just think about it. They add up to 15. Great. That's cool. Well, that means they each have essentially like a proportion there. So 3 plus 12 gave me 15. So that means 3/15 was 1/5. And 12/15 must have been 4/5. I want you to think of like a little exchange that's about to happen. The 3 ohm resistor will now get 4/5 of the current. And let's switch colors just to be fancy. Now the 12 ohm resistor is going to get 1/5 of the current. And it does that because, again, the least resistance gets the most current, and the most resistance gets the least current. So I could have looked at this already and said, okay, well, what is, switch colors one more time just for fun. Well, what's 1/5 of the total current? Well, that's nice. It's a 5. So what's 1/5 of 5? 1/5 of 5 is 1. So 1 amp would have gone here. What's 4/5 of 5? I suppose that's 4. So 4 would have gone there. And then one last layer of checking. What's 3 times 4? Oh, it's 12. What's 12 times 1? Oh, it's 12. So is that a harder way of thinking about it? Yes. But why does that matter? Like, why would you go through all that if it didn't count for anything? Well, the first thing you'll notice on questions on the AP exam, see if I can draw over this, is on a that's not what I wanted. On the AP exam would be they don't give you numbers, they just call them R. So let's see if I can find a way to blank this out. Alright, so I think I found a way to blank that out really quick. So what would you see on the AP exam then? Well, I'd see something about a voltage source. You'd see this squiggly E, which is an E that stands for EMF. They used to think voltage was a force that pushed the charge. Figured out later that it wasn't, so they kept the acronym. I don't know why. So EMF is another way of saying voltage, and that's the symbol for EMF there. But instead of saying like 12 and 3, they'd say R and, let's make up a number, 3R. So you'd automatically have to look at that and say, okay, those are two light bulbs. One's described as R, one's described as 3R. Really quickly, which one's going to be the brightest? And you'd have to say it's going to be R. Well, how would you know that? Because they're in parallel, these two branches get the exact same voltages, so it comes down to current. And so when you look at these two numbers, the one with the least resistance gets the most current. So another way of asking it would be, alright, Smarty, choose between A through D. How much brighter is R compared to 3R? And then you're like, oh Lord, I don't know, maybe 1/3 because of the R compared to 3R. Well, actually, again, because there are 4 parts to the current there, R plus 3R would give you 4R. Therefore, 3/4 of the current would go here. 3/4 of the current, let's actually call that 3/4 of I. And then this would get 1/4 of I. You could answer multiple ways. You could say, although they would get the same voltage V, you would get, say, a power of 3/4 power versus 1/4 power, because that was just I times V. Or you could say it's 3 times stronger. You could say it'd be 75% of a power unit. It would just depend on the way that whoever wrote the question tried to be tricky with their answer. So hopefully you listened to the first 2 minutes of this and got your final answer, and then saw where I was going with the last 7 minutes of it, where the idea of, if I ditch the numbers, can I figure out the proportion really fast? And you'll see that on the very next couple pages of your packet.